I'm giving this talk, but a lot of the work was done by Felipe Fernandez and Kyle Wilcox, who I've been working with pretty closely within the IUS program, and you can, hence the slide here that says Integrated Ocean Observing System. The USGS has graciously let me spend my time on IUS as a USGS contribution to IUS. So I'm working with these guys. They're actually should be probably, a long list of people, because there's a ton of people who are working in IUS to make the kind of things that I'm going to show you happen. So Philippe and Kyle specifically have been working under Sakura, which is one of the IUS regions. And okay, so today I'm going to start off by showing you, sort of giving you a high-level view, I guess, of why I think we're doing all this. I already sort of mentioned that a little bit, but there was an interesting, a few years back, there was this book called The Fourth Paradigm, talking about how there have been these different phases of the way science gets done, and that maybe 1,000 years ago, science was sort of empirical, descriptive. The last few hundred years has been, theory has come along, and then in the last few decades, computations have been extremely important, really doing full simulations of complex phenomena. And the concept was that today, there's this whole other branch of data exploration, sort of this whole big data, e-science stuff. But, this never really, to me, it never really rang exactly true. And I was cleaning out my office a few weeks back, and I found another article in this same book, in The Fourth Paradigm, that talked about this guy's essay was saying, instead of a fourth paradigm of science, all those things are really still important, right? And, empiricism, theory, computations, and data. But really what we should think about this is a need for a fourth network layer of data that sits on top of, we started out with the Ethernet, and then we have a standard protocol, TCP/IP, and on top of that, we built the web. But now, how do we access data in a very efficient way, get at the kind of information that we want to get to, and get the numbers back? So, in this article, which I actually highly recommend, you can grab it out on the internet, by John Wilbanks, called "I Have Seen the Paradigm Shift and It Is Us." He said we need an end-to-end, layer-by-layer designed information and technology that are composed of no more than a stack of protocols. We need open standards, and above all, we need to teach scientists to work in this new layer of data. So that's what I'm going to be talking about today, hopefully teaching you a little bit about how to work with at least one little component of this, what I would think of as this new layer of data. I think this is what I think we're doing. I think we're working on building this fourth network layer of data, defining these protocols and these open standards, and then teaching people how to use it. So that's going to be a job that we all need to play a role in eventually, I hope. So just a word about IUS. If you don't know about IUS, it's got 11 different regional associations. So here on the East Coast, we have Niracuz and Makura. It's part of an international system of organizations, and IUS is trying to take all the observations that are made by different organizations and all the models that are run by Navy, NOAA, regional associations, and create a system where all that information can be utilized to solve important issues that come up in the regions and make that data more available. So they're all about trying to figure out how to take all this sort of heterogeneous information and make it more homogeneous. So it's a nice place to work on these issues, which really are not IUS issues, but are much bigger issues for our whole geospatial community. Is there actually, now that I think of it, how do you guys want to ask questions? Is it, can you interrupt me somehow, or are you all in mute mode, or or you want to raise your hands on the, you probably are sitting around a table though, right? You can't raise your hands individually.
Well, yeah, the people on the phone are currently muted, but we can, should we unmute them? Okay,
well, yeah, why not? I mean, if this is meant to be informal, Why don't we
Sure.
try it? Why don't we try it? And if it gets too noisy, then we can.
Okay. All right. I probably have to do it individually. Which one? So. Okay. So we're unmuting everybody individually here, and sorry. One thing I also forgot to mention at the very start is we're also recording this presentation. So afterwards we'll have that recording available. But yeah, it looks like. We're getting a little bit of feedback noise here. Yeah, sorry, Rich. I think we'll have to keep everybody on mute because we're getting a lot of feedback noise. Can we have people in here in the room that
You always can type in the question from the chat.
Yeah, so why don't we do that? If there are questions that come up on the chat feature on the webinar, the people on the phone can post a question there, and we can also put questions out there from here in the room along the way. Otherwise, we'll also have questions at the end.
Also, we will unmute everybody at the end of the.
Make sure it's Rich. Sorry, Rich, we muted you. So we'll
Okay.
go to the mic and speakers up above. Attendees, sorry. Scroll down. He's probably down below. It's all alphabetical.
That. Oh yeah.
Okay. Sorry, Rich. Are you there?
That's it. Yeah, I'm here. Yep.
Okay,
Just watching
we're back.
watching my little microphone, waiting for it to turn green again. Okay. Anyway, so I was just saying that it's a nice environment, a little microcosm, really, of the issues that we have throughout the larger geospatial community, I think. So, to play in IUCE, if you're a data provider and you want to be part of IUCE, you have to provide a web service. Okay, so whether you have observations or models, you have these web services, and there's specific services that they're named for each type of information product that they want to support, like models. So for models, we have these kind of models, which have curvilinear coordinates in the horizontal. This is like a ROMS model or a POM model, of course. And in the vertical, as you know, we have these stretched vertical coordinates that can be sigma, they can be S coordinate, they can be sigma over Z, all sorts of stuff. We also have these unstructured grid models, so from things like Schism or AdCirc or FVCOM, where we have triangular or even combinations of tris and quads. So how do we represent those in a common way? Well, as you probably know, we have the CF conventions that describe how you attribute your files in a way that it makes it unambiguous to find the latitude and longitude and to describe your time coordinate and to describe your vertical coordinate. And this has been in use for many years to standardize, so you can write your netcdf file in a bunch of different ways, call your variables different things, but as long as you have the right attributes, it can be understood by software that reads and understands the CF conventions. So we have the CF conventions, but they are designed for regular grids, and so we've also, if you Google searched on UGrid conventions, you'd find a web page that talks about unstructured grid conventions. So which attributes you need to put into your unstructured grid files for software to be able to uniquely find things like the connectivity array that describes how the little triangles are all wired up. And we've also just recently introduced this S-grid convention for describing how things are on a staggered grid. So in ROMs, for instance, as you probably know, on your staggered ROMs grid, the U and V points do not have vertical coordinate information specified at those points. And if you wanted to draw a velocity vector, you have to average them to the grid cell centers or the grid cell corners and then rotate to east and north. So how do you codify all that in attributes? And that's what the S-grid does. I'm not going to dive into these today because I think that could end up being a long time. So we might, if you guys are interested in sort of diving into these U-grid and S-grid conventions, we could do that at a different seminar. But today I'm just going to show how you can use those things once you've actually done them added that attribute information to your modeling products. I'm not really going to talk about time series and trajectories, but I wanted to leave this slide in here just to remind me to say that although those CF conventions were developed really for model output, they were so useful that they've been extended essentially to cover discrete sampling geometry, as they call them. I prefer to call them sort of scientific feature types, and those feature types are trajectories, profiles, time series, swaths, radials. So there's different, we don't have hundreds of different data types in physical oceanography and oceanography. We have, a handful. And so for each one of those types, we can define a common data model that then can allow us to do a lot of interoperable merging of information from different sources in a convenient way taking advantage of software. So this is just what the gridded data for IUs, you deliver it through OpenDAP with these CF conventions and now also with UGrid and SGrid. And images of data, we typically, IUs serves via web map service, and for these in situ data through this OGC sensor observation service. So on the back end, you can have your NetCDF files or some other kind of files with your sensor information, but if you have them in the CF convention format, then you can deliver them through a sensor observation service very easily. And you can do all this stuff using the Threads data server, which is not the only way to do it, but it's a really convenient way. So you have your piles of files over here of all your ROMs history files, and if you wanted to make it UGrid compliant, or actually, well, in the case of ROMs, say you wanted to make it SGrid compliant and aggregate all those files together, you can do that with a little bit of NCML, which is just a text file with XML markup. So you can virtually aggregate and standardize your collections of data into this common data model. And then once it's in the common data model, internally, this means in memory, you can have all these services that just work as part of the Threads data server. So you can deliver it out through OpenDAP with CF conventions. You can, for time series data that's in CF convention, you can serve it out through a sensor observation service. There's a web map service that's already enabled for structured grids for CF compliant data. There's also this NC ISO service, which takes all the attribute information that was in your files and that you've provided here in this NCML, and turns that into ISO metadata through a mapping that you could go read about. So if you want to know how your attribute and your NetCDF file ends up in an ISO metadata record here, you can go look at that. But what it allows you to do is then you create this, a modeler just throws a whole bunch of data files into a directory. You have this little NCML that creates this virtual aggregation, and you get out an ISO metadata record that can be sent off to places that provide these catalog services like CCAN, PyCSW. This is what data.gov uses. So if you want to think of it that way, your data could just be sent to data.gov, although we all have procedures for how that happens. And a variety of this ISO metadata can be consumed by just about any catalog service. So then you can query these catalog services to find data. Okay. So when you have these services, you can build all these different clients that access MATLAB and Python and ArcGIS that consume data from these standardized services to do cool things for, so if you're a MATLAB person, then you don't have to worry about whether it was ROMs or NCOM or HICOM. All you can just access this open DAP with CF convention stuff and make use of it in your application. So just one example of, so you get all that ISO metadata out. So we have all these thread servers all over ICE, and they're all producing ISO metadata. You collect up that ISO metadata, you harvest it every night, and you put it into this, in this case, a GeoPortal server that's running at NGDC. And so all the metadata is in here from all these thread servers. So you can say NECOFS or SOS and temperature, and you get back a list of data sets here, and you can click on one and see which region it is. And notice that there's an OpenDAP link here as well. So if you wanted to, you could go to this GUI and do searches once you figure out what the search syntax is, like putting parentheses around things that you want to OR and then and star temperature and things like that. You could do it this way and read a little bit about the data sets and see where they are. But at some point you probably just want to do this stuff programmatically. And that, I think I'm going to save most of this catalog programmatic stuff for another talk, but I just wanted to mention it here. So another thing you can do then is you can build these web portals that actually consume the web map services. So you can do a query on that catalog and find out all these model results that have web map services, and then basically let users poke around and change the color map. And here I'm looking at some model output from West Falmouth Harbor. This is a portal that we paid a consultant to build for us. So the software behind it is not completely, although all the products that are displayed on the map in this portal are open and free. The software itself that makes that you are running when you run this is not completely, it's open source, but it's not really documented, or it's not out on GitHub. And so basically when we want something changed here in this, we basically pay this consultant. But it's pretty nice. You can click in a spot and get a time series, and all this is coming from those services that we enabled, and you can move the time slider along here and get different, see the model output at different times. And of course, the most important thing is we can change this color scale to be whatever we need it to be, and change it to be log scale or whatever to look at the phenomena of interest. So this is all just browsing images of the data, not the actual data, getting the actual data itself. And this is just an example of doing this in data.gov, then one of those data sets that's made it through into data.gov. We can actually do a search, find the data, and then bring up the data.gov map viewer and click on now significant wave height from our, this is our coast forecast model that we run at USGS. Okay, but really, for probably most of the folks in this room, you don't really want to look at pictures of data, you want to actually get the data. So we have a thing called NC Toolbox for MATLAB folks, where this is an example of doing a query. Actually, I went to NATO last fall and set them up with these tools so that they can do a little query across all their model results and find all the model output that was in a particular region and time, which was actually their a big field campaign that they did to compare a whole bunch of data and models together. And then they were able in MATLAB to just pull up those different models. So these are 4 different models that are running. This is Mercator and a Mediterranean forecast system over here, and an NRL model over here, and a ROMS model over here run by a regional association. But before this, and so you just issue the same command, and accesses all the data from these different models in a common way. And so they were super happy about that, because before they were just wandering around with hard drives, and trying to compare data was, people were using like NC View opened in 2 different windows and things like that. And it was just, so this was really helpful to them. But I'm not going to talk about MATLAB today, because remember I said free. So at this point, oops, I think I had one more slide. Oh, okay. Oh, there we go. Okay, I skipped this slide by mistake. So I want to talk about accessing this data in Python, because Python is free. And it's it used to be that Python was a real pain in the neck to install and get all the packages installed that you needed, and sometimes it didn't work on Windows and all that kind of stuff. And we've really been working hard, or actually Philippe has been working really hard to take advantage of advances that have come along in the Python community, most notably the Anaconda Python distribution, which you can just do a sort of single click install on any platform. And then we've been packaging all these different modules that you might need to do all sorts of different things as a collection that you can just, then you can create an environment that has all those packages with just a very simply and get up and running these kind of complicated notebooks. In this case, this is we're comparing two different models that, again, using in Python the very same command, but here we're accessing a ROMS model with this URL, and we're accessing the RTOFs model from NSEP with this URL. And we're just saying, hey, give me the latest seawater temperature data, and get back, and then we get back the data, and plot it up. So even though we're looking at images here, we have the data then locally in the, we're actually displaying the data in the browser. So at this point, I want to give a little demo of how this stuff works. I want to convince you that you could go back to your office and run these notebooks. So I want to show you how that's done. So I'm going to jump out of this right now, and let's see. So I made I'm a big fan of GitHub. So if you go to my, if you Google rsignal-usgs, I think you're going to land on my GitHub page. So it'll look like this, and you can see that I've been a real GitHub fan for at least a year now. So I pretty much do everything on GitHub. But if you, and so I actually made this little repository just this morning called I Use Training. And this is sort of the steps that I'm going to show you. And so if we don't get through them, or you don't have to take notes or anything, because they should be on here. And if you get stuck anywhere, you can, here it says if you have problems, see the issues page and click the green new issue, new button. Actually, does that? Let me see if it should work. Wow, it's kind of slow. Anyway, new issue over here. Okay, so back to this. So here, there's a PDF of my slides here, but the first thing now is then to set up the iUse environment. So I'm going to do it on Windows, but it's exactly the same on Linux, and it's very, very similar on Linux and Mac. So you can do it. You should be able to do it on Windows, Linux, or Mac. And so step one is follow these instructions. I'm going to open this in a new tab here. So here are these instructions also on GitHub. But you can read about why we're suggesting the iUse Anaconda, the iUse environment with Anaconda. The first step is to install Miniconda, which is basically the base Python distribution from which you can then create these custom environments. And so this, instead of going and downloading the full Anaconda package, which is up here, which installs all sorts of packages that you don't really need, why not just install what you need? That's what we were thinking. And it's faster to download this. I'm not actually going to download and install this right now. But it's pretty quick. But I've already installed it, so it'll be kind of boring. But what I am going to do is, once you've got it installed, this part here, create the iUse environment, I'm going to show you, plus some of you may already have this installed. Anyway, so if you have Miniconda installed, then when you go, you'll see something called an Anaconda prompt here. And if you open that up, you just get a good old command window. So the next step is to download this environment.yml file. I'm going to open this up in a new tab also. So if you look at this, probably can't see that too well, but this is just a list. So I'm going to build an environment. This is going to build an environment called iUse, and it's going to download packages from an iUse channel that we've set up, and it's going to install all this stuff here. So it's going to install a bunch of stuff. but you can see some of this is like PySgrid. So that's a Python package we made for dealing with SGrid. Here's PyUgrid that's dealing with PyUgrid, and so on. So there's a bunch of stuff that's going to install, but you don't have to go do this yourself, right? So I'm going to do a right mouse click and save as. I'm going to save it as environment.yml in my downloads directory. So now, can you see this okay? Can somebody confirm?
Yeah.
Okay. Yeah, so, and then typically, what happens with Windows, of course, it renames stupid. It does things like renames your file with .txt, so I don't really like that. So I'm going to go take the txt back off. I should have clicked the all files thing. So again, I've got it now in my downloads directory. So back to the instructions here. So now that you have, maybe I'll make that a little bigger. So now I can type, I've got Miniconda installed, so I can type conda in that Anaconda window. I'm going to say, create this environment from that file. That's all I have to do. So I go back here, I say, conda, actually I have to go to that directory first, right? Downloads. Oh, I love the command line. Conda env create environment environment.yml. So I hit return, and it's going to go off and actually fetch all those packages from our iUse channel that have been compiled. It knows what machine I'm on. So if I'm on like a 64-bit machine or 32, or I'm on Linux, or I'm on a Mac, it'll download the appropriate packages for my platform. Okay, so you can see it's going through and bringing down all this stuff. So Python, netcdf is in there, actually netcdf 4, because you can see the HDF5 libraries coming down, some cool plotting stuff, the Jupyter console, which I'm going to show you now. So that worked. So you see at the end it says to activate this environment, type activate iUse. Well, I could type activate iUse here on the command line, and then I'd have, and maybe I'll do that actually, but well, I'm just going to plow ahead because I don't really want to do stuff from the command line or a terminal. I want to, if you follow the instructions, you'll see if I type launcher, I come up with this nice little graphical environment where I can just select the environment that I want. So iUse, here's the new one we just made. So I click on iUse. And so for the iUse environment, I have these things available. I could install these other ways of interacting with Python, but I just want the IPython notebook. So I'm going to click that. And so now I'm actually running in my browser. Okay, I'm communicating with a server that's actually running locally. So in the beginning, I was saying about how it's nice to not have to install stuff, but yet I just installed stuff, right? But I'm doing that because, for one, actually, you can do that. You can install this stuff without system admin, so it doesn't need any system, it doesn't need any system level permissions to install for you, a local user. Everything is self-contained in a particular directory. If you say, I can't install anything on my system, because this is a server web client communication kind of thing, you could install, like, as an organization, you could install the server as a multi-user server on a system close to your data, so that the users can just communicate with their and use everything from their browser, but the server, instead of being local on their just machine like like we just installed, would actually be running on a machine at your data center, and or somewhere else that you didn't have to maintain, and would not actually be on your system. You'd just be interacting through your web browser. So let's see. So I have so here I have this iUse training repo, and if you go back to the instructions, you'll see that I have some notebooks here that I made as part of this little IU's training repo. And if I go into that notebooks directory now, the first one I want to run is that one that we were just looking at, which is accessing data from IU's models that are all CF compliant. Okay, and then there's a little thing here. You can run this notebook using IU's Anaconda IU's Conda environment, which links back to those instructions we just looked at. So I'm going to, we could just look at the output, but I'm not going to show. I'm going to actually make sure that, just to prove to you that we're running this live, I'm going to clear all the output. And let's just, I can restart the kernel, which basically is saying, hey, give me all the latest stuff from the environment that we're running, just to start off sort of cleanly. So now this is my browser again, and again I'm communicating with Python running on a server. In this case, it's running on the same machine. But the notebook is kind of cool because you can combine. This is just some text that I've indicated as markdown in this cell. I don't know how familiar you are with these notebooks, but and if I execute this cell by hitting Shift-Enter, it renders that text nicely as HTML. In this case, I'm in a code cell. Maybe that's hard to see. And if I execute this cell, it just goes ahead and imports these libraries from, and comes back and says, okay, I completed the first cell. So if I keep doing that, now I just have some functions here that help find the nearest time variable. And here I have something that actually, I give it a URL and a variable and a time step, or a time that I'm interested in, and a level, and whether it's subsampler or not, and it comes back with a data slice. So I'm just going to execute these functions here. This one makes a map, and now here I'm selecting a time that I'm interested in. So let's just say we want the closest time to now, and so I'm going to keep executing this, boink. So the closest time to now is that time, and that's UTC time, obviously. Okay, so now here's a bunch of cells that are all exactly the same. So they just say model, URL, well, almost exactly the same. Variable name, or the standard name that we're interested in, which level we want, and then we just say get it and map it. And in this case, it's coming back with some warnings because we're using the British Met Office package called IRIS, which is the CF package for that we're using for Python, and it's very strict. So it comes back and tells us, I didn't find I found the formula terms here, but the dimensions, blah blah. I don't know. Yeah, you can read all this stuff, but basically those are just warnings, and it retrieved this slice and has displayed it here in this plot. So again, the browser is sending the commands back to the server. The server is actually doing the computations and then delivering the image back into the browser. So we just got that one, and if I go down to this cell, so here's some espresso data. If I hit Shift-Enter here, it's going off to the server. It's loading the data from OpenDAP and bringing it back into IRIS and plotting it, and here's Marcus. So we can go cell, run all below, and just fire it off, just to prove that now we're hitting data from all these different places, right? So from UCSC, from Hawaii, from Hawaii, and then at the end from Global RTOF. So, and again, these are just some models we're accessing level 0 because it's 0 is at the surface, and sometimes we're saying -1 because it's at the bottom, or 1 because 0 has got nothing. And this could of course be abstracted away also. But anyway, the point is that if you've got your data in CF conventions and you've got it out there in a thread server, you can access it in Python in free software. And now we've got the data from all these different models, right? So we can interpolate them onto a common grid or whatever if we wanted to do detailed comparisons or compute the area of whatever temperature and the average temperature in the Gulf of Maine or something like that, because we have the data. And and here I'm just, this iris package is pretty cool. These things that we're loading, I'm realizing now this is a lot of, this is covering a lot of ground in a really short amount of time. So, but maybe that's okay. If we could come back and drill into any of these things in more depth in a, if you wanted to say, yeah, tell me about iris, this iris package, we could do that at some future date. So I think for now I'm just gonna, I'll leave it at this. But this data that we extracted, it's got this so-called cube that we plotted. We were plotting this thing, this cube here. This cube has all sorts of properties and methods that you can calculate on it. But if you just say print it, it comes back and it gives you all the attribute information and stuff like that. And it tells you this particular slice that we cut out is this particular time and so on and so forth. It found the latitude and longitude like we expected it would, and so on. So that's for CF compliant data. So so let's look at another one. So let's open this one. So this is actually, let's open this one. This is unstructured grid stuff. So here's the same kind of thing, except now we're going to use PyUGrid as well as iris. So iris itself does not support unstructured grid, but we made a package called PyUGrid that then can go work with data from AdCirc or FVCom or Selfie and find the connectivity arrays and whether they're on the face or the cell center and stuff like that. I mean the face or the node. So if we do the same thing here, let's clear all the output. Clear all the output and restart the kernel, although we really don't need to restart the kernel. But so again, if we, let's see here, let's go through some blank, doink. Okay, actually, so I've got this, here I've got this set up to read some AdCirc data from this URL here, which is some data from the IUS testbed. So some Hurricane Ike data, okay? Again, this is just a URL, an OpenDAP URL. And again, it's, I guess, did I already execute that one? Yeah. Actually, so you can see it only complains the first time. It gives you those warnings. If you wanted to look in those warnings and fix up your metadata some more, you could. So here it's actually calling PyUGrid. It comes back and says there's this many faces and this many nodes. And here we're actually just creating a triangulation object so that we can use Python's tricontour to plot up the data. So a little bit off the screen here. So here we've just grabbed this data for this region, and now actually I'm showing you that not only can you just look at a plot here, but you can actually zoom in on these plots. Even though we're in a browser output cell, we can zoom in on a particular region and see what's going on in more detail, even though we're just, again, in a browser cell. Okay, and just for fun, just to show you that, so yesterday I've been working with the guys at well, I think it's CSDL. Who's running STOFs? I guess you guys are running Are you running STOFs? Anyway, yeah. Oh, okay, so just yesterday they told me they have this aggregation set up. I've been working with them to set up an aggregation of STOFs data. So if we switch this URL to STOFs, and I guess we can stay down in the, let's comment out this bounding box for the northern Gulf of Mexico and change it to something like the Gulf of Maine. So up in my region, and then we can change the levels to be from, instead of from -1 to 5, to be -3 to 3. And then actually, unless there's a forecast model, right? So let's do now, and then let's do like 6 hours from now, or let's maybe do 12 hours from now, or maybe 24. It doesn't matter. Okay, it doesn't matter. We do it 24 hours from now. Okay, so this should come back and let's see, did I? Okay, so notice too, when I execute that, it comes back and it says, these are not necessarily in order, right? They're just the it's not like 1, 2, 3. It's 1, 2, and I did a bunch of other stuff, and now I came back and hit this cell again, and now so it's step 15, right? So so I can go down here, and now this should come back with some different information. So this is Estof's contact Yuji Funakoshi. I don't know if that's right or not. Hopefully it is. Anyway, bunch of other information, and then if we just keep plowing ahead here, this should work if it's UGrid compliant. So we're waiting. It's retrieving the data from the step, and let's see, it's kind of a bigger model, I guess. So there we go. So that's the, so that's the 24 hours from now, the forecast water levels in the Gulf of Maine region for Estof's. Pretty cool. So let's see, so what else? Maybe one last thing is, what do I got one more. Okay, so I've got this, oops, no, I don't want to open the Python. Actually, these are Python versions, just pure Python versions of these same notebooks, just because if you wanted to run these yourself, in a script or something, you'd want to run these things. So when we modify these, we have our notebook settings set up to automatically save a pure Python copy every time we modify a notebook. And that's the instructions for how to do that. If you want to set your stuff up that way, is also on that IUse page. But this PyScript example, I guess I wanted to show because I'm just going to go ahead and run this one, all of them. So I'm running it, and it's coming back, and basically it's using this PyScript. I'm not going to get into the details of this right now because we're kind of running low on time. But basically, this is pulling velocity data from a ROMS model and doing the grid cell centering and rotation, but without any specific ROMS stuff going on. Like it's not, so it's just using the SGrid attribute information with this PySgrid library. And so we have these routines called